So, strangely enough, real numbers are not everything that is necessary to solve problems in a lot of fields like electronics. Um, and what happens is we get a lot of solutions that have these things that have imaginary numbers in them, things that we're going to call imaginary numbers. And other times, it's easier to work in imaginary numbers than it is in the real number system itself. So let's talk about what makes an imaginary number. So in these fields, we end up with things that have negative square roots, which are technically undefined in the real numbers, which makes sense because we know that things like the square root of 3 squared is equal to 3, the square root of 9. We also know that the square root of negative 3 all squared is also equal to 3, because when you take the square root of a number, you talk about the answer as being its principal root. So the principal root of negative 3 squared is still positive 3. But in either case, these are the square root of 9. Oops, can't write that. And the number underneath the radical generally has to be positive. So they had to come up with a way of dealing with these square roots of negative 1 because they kept cropping up in their work. So what they did was they just gave it a letter, and they said, let's let the square root of negative 1 equal this I, and we'll call this I an imaginary number. Definitely not real. Okay, so this is the definition of what an imaginary number is. So here's how it works. Generally with square roots, there's a law that says the square root of a times the square root of b is equal to the square root of a times b. But this law has a requirement that a is a positive number and b is a positive number, or 0. They could be equal to 0 too. The square root of 0 is just, well, 0. But then the problem becomes, what if it's negative? So there's two ways this multiplication of radicals works. It works in the direction that I have it written, but it also works in the other direction. If I can create a square root of a factor of numbers, or the product of numbers, I can separate them over a square root. But again, a and b have to be positive. So for example, let's say I have the square root of negative 6 times the square root of negative, what's a good one, 30. So what we'd have to do first, before we could even, use those properties of square roots up here, is we can't use them unless the two numbers are positive to begin with. So we're going to have to separate these as negative 1 times 6 and negative 1 times 30. At least mentally in your head, the step you might not want to write out. So this becomes the square root of negative 1 times the square root of 6. Oops, that should be a times the square root of negative 1 times the square root of 30. Okay. So when we do this, the square roots of negative 1s are now free, and we can write this as I square roots of 6 times I square roots of 30. Okay. Then when we multiply them, we're going to get the square root of 180, because now I can, oh, wrong one, I can multiply them together. And then what gets weird is this I times I, algebraically, becomes I squared. So we have to figure out what to do with that term, right? So let's figure out what to do with I squared. Now remember, I squared is the same thing as I times I, which is the same thing as the square root of negative 1 times the square root of negative 1. So what happens if I have the square root of 5 times the square root of 5? Well, that's equal to the square root of 25, which is just equal to 5. The square root of 7 times the square root of 7 is equal to the square root of 49, which is equal to 7. So if I have the square root of n times the square root of n being a positive number, the answer is just going to be n, with my little caveat that n is greater than or equal to 0. So it kind of follows that the square root of -1 times the square root of -1 is going to equal, by our definition, -1. So we're going to let I squared equal -1. So anytime you see an I squared, we're going to replace it with a -1. So that I squared becomes -1, and this becomes the square root of 180. All right, now that leads us to another thing. The square root of 180 is generally too big, and we have to reduce the radical. So the way I reduce radicals is I'll take the number, and I will divide it by the smallest number possible. Now, obviously, 1 is going to go into it, so it's kind of a trivial solution. If it's even, 2 is definitely going to go into it. It'll go into it 90 times. 90 is even, so 2 will go into it, and that'll go in, 45 times. And let's see, 4 plus 5 is 9, so 3 will go into it, because 3 goes into 9. It's a neat little trick. That'll be 15, and 3 goes into it. That'll be 5. So then the square root means you're looking for pairs of factors. So if you have two 2's on the inside, it becomes a single 2 on the outside. If you have two 3's on the inside, it comes out as a single 3 on the outside. And I'll bring that negative down, and a square root of, and the only number left, because you only have to look on the L if you do the smallest factor trick, the only number left on my factor tree is this 5. So the negative square root of 180 is the same thing as negative 6 square roots of 5. And that would be our final answer. So I kind of use this example to go through a few things, pulling out the negatives as I, multiplying things together, getting I squared, and showing you I squared is equal to -1, and also showing you how to break down a radical. So I kind of covered 3 things in one ugly example. All right, so now on to the main topic, complex numbers. Now, complex numbers are literally just a real number plus an imaginary number. So when we write it, we're going to have a standard form, and the standard form is a plus bi, where a and b are real numbers. So we could have things like 4 minus 3i is a nice complex number. We could have things like the square root of 2 minus I square roots of 7 is a nice complex number, though not pretty. One thing to notice is the position that I put the I in depending on what kind of number I'm dealing with. 3 being a rational number, I'm putting the I to the right of it, whereas the square root of 7, I'm putting the I to the left of it. Now that's legal because, commutative property of multiplication. And the reason I do it with the square roots is sometimes people draw their square roots a little bit long and they cover more than they should. And it becomes ambiguous whether the I is under the radical or you're not quite sure. So by putting it in front, you're guaranteeing that the I is shown where it properly is, which is outside of the square root. All right, so when we deal with this first piece, the A part, this is basically just the real part of the number. And then this part is the imaginary part. So we have a real plus imaginary. Okay, so generally when you write a complex number, you want to write it as a plus bi. Now, 5 is a complex number. It doesn't seem like it because, it's a rational, real number here. But I can always add on 0 times I, because 0 times I would be 0, and 0 plus 5 is just 5. So 5 actually is a complex number if we want to think about it that way. The same reason that 4i is a complex number all by itself, even though it's strictly imaginary, because we can always add a 0 as the real part. So technically, every number we've ever dealt with is a complex number. Now that we've defined what a complex number is, we should be able to do operations on it: addition, subtraction, multiplication, and division. So let's start off with something simple. If you have something like 4i plus 7i, then we should be able to add them together because they have like terms. So by the distributive property, we can kick the I out, kind of like factoring, and left behind is 4 plus 7, so therefore this becomes 11i. Okay. So if you have two I terms, you can just add them together like we do with x terms. So I, in a way, is like a variable, except it's a constant. All right, so if we have something like 2 minus 3i minus 4 plus 7i, we can treat it as two binomials that are being subtracted. So the first step is, get rid of all the parentheses. So the first one just has a positive 1 in the front, so when I distribute the positive 1, it doesn't change anything. The second one has a negative 1 in front, and when I distribute, it's going to change the signs of the things inside. So I'm going to get negative 4 minus 7i. And then by the associative property and commutative property and all that fun stuff, we're going to get down to the real part minus the real part, plus, and I'm going to just be emphasizing here, the imaginary part plus the imaginary part. Now this is a step that you would normally do in your head. So you'd get 2 minus 4 is negative 2, and negative 3 plus a negative 7 is a negative 10i. So we would get this nice complex number. So when you're adding imaginaries, you get an imaginary number. If you're adding two complex, you get a complex number. And just remember, all numbers that we've ever dealt with are complex. So even if this turned out to be negative 2 is still a complex number. All right, so addition and subtraction is not that hard for complex numbers. Most people have trouble with multiplication. So for example, if we have negative 3i times 4 minus 7i, we're still going to treat this as a monomial times a binomial and distribute. So we're going to get negative 3i times 4, and I'm going to, again, just write this all out so you can see all the pieces, and negative 3i times negative 7i. So it'll be plus negative 3i times negative 7i. And then we're going to use our good old commutative property to get things that I can multiply together closer, and the i's I'm going to try to push off to the far right. So this one is going to become negative 12i, negative 3 times 4, and then back to times I. And on the other one, I have a negative and a negative, so I know the answer is going to be positive so far of whatever comes next. And then 3 times 7 is 21, and I times I is I squared. Now sometimes when people see this setup, they think of the distributive property, but you really shouldn't, and you definitely shouldn't think of FOIL. All that's going on there is a reorganization of the numbers so that we, get the negative 3 next to the negative 7 and the I next to the I. That's all that's going on. It's not the distributive property. All right. And then we just have to remember that I squared really is the number negative 1. So we get negative 12i plus 21 times negative 1. So that's going to turn out to be negative 21 first, so I have the real part on the left, minus 12i second, the imaginary part on the right. And I try to write I as the last thing possible unless there's a square root involved. So that would be a imaginary number times a complex number, and of course we ended up with a complex number. All right, so let's do something a little bit weirder. What if we had negative 4 plus the square root of negative 21 times 5 minus the square root of negative 15. This is going to get messy. All right, So if they're not in terms of a complex number to start off with, without that I, but you see a negative underneath a square root, you're really going to have to deal with the I first. So when I write this the first time around, I'm going to go and write I square roots of 21. And over here, I'm going to write minus I square roots of 15. Okay. And then I'm going to, FOIL. There are two binomials. I'm going to distribute it out. So negative 4 times positive 5, that'll give me a negative 20. A negative 4 times this negative I square root of 15 is going to give me a positive. I highly suggest you always go for the sign first. Negative times a negative is a positive. And then the 4 and the I are going to multiply each other, but you really can't do much, so you're just going to write 4I, and the same thing with the square root of 15. All right, so that would be the outer. Inner, we're going to get 5I square roots of 21. And then last, we're going to get a positive times a negative. That'll be negative. We're going to get an I times an I. That's I squared. And we're going to get 21 times 15. So this would be 315 square rooted. All right. So then we can try to simplify from here. The I squared becomes negative 1, so this whole term becomes positive. So that's going to be negative 20 plus the square root of 315. That's my real part. I said this wasn't going to be pretty. And then the imaginary part is the things that have the i's left behind. So the best I can do is to factor out the I, way over here to the very far right, and leave what's behind. So it's going to be 4 square roots of 15 and 5 square roots of 20, and they're both positive. 21. All right, and that's the imaginary part. Now the only thing that might be a hiccup is 315 might be reducible. So I'm going to go off to the side and write 315 and find the smallest number that'll go into it. So let's see here. 5 plus 1 is 6. 6 plus 3 is 9. So 3 will go into it, and it goes into it 105. All right, and then 1 plus 0 plus 1 is 6, and 3 has to go into this also. And it goes into it 35 times, and 35 is just 5 times 7. So I can pull out a 3. So this becomes negative 20 plus pull out the 3, leave behind that 5 times 7, better known as 35. And there's my real part, plus, and there's nothing I can do with the rest of it. And there would be the product of those two complex numbers. Not pretty. So the division of complex numbers is where most people get kind of stuck. So for example, let's do a simple one. A complex number, 4 minus 3i, divided by 2i. All right, so we could do this individually or we can do it all together. I think it's quicker all together. And you just have to remember that I is a square root of negative 1. So what we're trying to do technically is rationalize the denominator. Get the I out of the bottom and bring it into the top. Now 2 by itself is a rational number, so I really don't have to worry about the 2. So to rationalize the I, kind of like with square roots, I'm going to multiply it by itself. And if I multiply the bottom by it, I'm also going to multiply the top by it. So I'm going to distribute in the top an I and multiply in the bottom by an I. So this will give me 4i minus 3i squared over 2i times I, which is 2i squared. All right. And then I squared, you just have to keep it in the back of your mind, is negative 1. So this is going to become 4i. Negative 1 times negative 3 is going to be a positive 3. And in the bottom, we're going to get a negative 2, because that I squared is negative 1 also. Now, I want to write it as a complex number, of the form a plus bi. And I really, really want to be the last thing that I wrote. So I'm going to distribute the negative 2 in the bottom to the two pieces in the top. That's legal because this is the same thing as -1/2 times 3 plus 4i. So the distributive property is still there. You'll find that making that number in the denominator a fraction in front comes to be a nice handy trick if you get confused about weird expressions in fraction form. So now I can distribute and I get -3/2 minus 2i, and that would be my answer. So 4 minus 3i divided by 2i is the same thing as -3/2 minus 2i. And it's in standard form of a complex answer. All right, so the problem comes when we put, or flip this fraction around actually. So what if I wanted to do the reciprocal? 2i over 4 minus 3i. Well, then we're going to have to play a small game. And the trick is going to come from what we just learned previously in the factoring section of the difference of perfect squares. Here I have 4 minus 3i. And if we have a difference of perfect squares like, x minus 2 times x plus 2, and we FOIL it out, we're going to get x squared plus 2x minus 2x minus 4, and the middle two terms are going to cancel. And we get the square of the first term and the square of the second term. So we're going to use this idea that the two middle terms are canceling, and we're going to call this thing that is different than 4 minus 3i its conjugate. So I'm going to write that in here in a second. This is called a conjugate. And it becomes really important later on to recognize what a conjugate is. So if I multiply the bottom by 4 plus 3i, and before I go further, notice that only one sign is changing, the sign between the 4 and the 3. If you change both of the signs, you're not finding a conjugate, you are finding an opposite, and we don't want an opposite in this case. And if you multiply the bottom by 4 plus 3i, you better multiply the top to keep this value as a 1. Multiplying by 1 doesn't change anything. Same thing for the 2i's up above in the last example. Alright, so we have this conjugate. We're multiplying top and bottom by it. In the top, we just need to distribute to get our answer. And 2i times 4 is 8i. I'll write it over here. And 2i times 3i is going to be 2 times 3, both of them positive, and I times I. And again, that is not the distributive property, that is commutative property. Alright, in the bottom, we're going to FOIL it out, and you're going to get 4 times 4, which is 16. And then the 3i and the 4 and the -3i and the 4, those are the two things that are going to cancel out. So I don't need to multiply them. And then 3i times 3i is 9i squared. And it's a negative times a positive, so the first thing I'm going to do is put that minus in there. And then it's going to be 9i squared. Alright. So the last step is getting rid of the I squares and reorganizing this so it looks like a complex number. So the I squares, they both turn into -1, so you get 8i plus 6 times -1, all over 16 minus 9 times -1. Alright, the next step, I'm going to get the I in the right location. I'm going to push it to the far right and simplify some stuff. So -1 times 6 is -6. That's a positive 8i, so I got the I in the last slot, all divided by 16 plus 9, which is 25. Alright, and then I'm going to use that trick up above where I distribute that 25 and write it as a complex number. So it's -6 25ths plus 8 25ths I. And there's our answer of 2i divided by 4 minus 3i. It's kind of a neat process, this idea of rationalizing the denominator because I is a radical. So just a preview for those that are going on to Math 172. In Math 172, we're going to be able to take a complex number and raise it to an outrageously high power. And we won't have to write it as a plus bi times itself 7 times, and then lots and lots of foiling and distributing and all that fun stuff. The other thing that's kind of cool is we're going to be able to take roots of these complex numbers, like a cube root of a complex number. But those both require trigonometry to be able to solve. That's why it's being put off to Math 172 when you learn about trigonometry.